Okay, so previous day we will first discuss whatever we study in the previous day, then we will go on discussing the today's topic. Now in the previous day, whatever we have discussed, I am just recap all this. Now previous day we have discussed the open loop configuration of the op-amp. This is the open loop configuration of the op-amp, and within the open loop, that means no feedback. First we have discussed the no feedback path. Okay, so in the case of the open loop configuration of the op-amp, first we have discussed the differential amplifier, second we have discussed the inverting amplifier, and third we have discussed the non-inverting amplifier, and next we have discussed the feedback. And in the case of the feedback, first we have discussed what is the positive feedback, what is the negative feedback, why we require the feedback, and then we analyze the importance of the negative feedback. Now whenever we discuss the importance of the negative feedback, first we study, then first we see that it actually stabilize the gain. First we discuss that it stabilize the gain, and second point is negative feedback, or the advantages of the negative feedback is increase the bandwidth, and third point is reduce the distortion. As the waveform is not, that means the purpose of the amplifier is that if the input waveform is like this, the output waveform shape is not changes, it only amplifies the magnitude. Okay, shape is not distorted. So in the case of the negative feedback, the distortion will not happen. Okay, so that is the advantages of the negative feedback that we have discussed. Positive feedback does not possess all these qualities of the negative feedback, but one of the disadvantages of the negative feedback it actually reduces the gain, and that is also advantageous in the case of the op-amp, because op-amp gain is infinite. So if we apply the negative feedback, the infinite gain is going to reduce to the finite gain, and in the case of the finite gain we get the, if the gain is infinite, you always get the saturated output voltage, that means V saturation or minus V saturation. But if the gain is infinite with the application of the negative feedback, then we get a proportional output voltage which is proportional to the input voltage, and that is the main function of the amplifier. Next, this is the two equation that we have derived in the previous class, that the amplifier equation, whenever we get the amplifier equation, that means the V0 by Vin, that means gain is equal to A divided by A plus 1 beta, and that is the case of the amplifier, and that is the equation for the negative feedback. Okay, and that is the equation for the negative feedback. And next we have discussed this equation. This equation is for the oscillator equation. This oscillator equation also be called as a positive feedback, because positive feedback, application of the positive feedback is oscillator. Okay, and we have also derived this equation. Okay, now moving on from the previous discussion, today we will discuss the concept of virtual count. And I have said previously that if you know the concept of virtual count, almost Opamp 90% of the problem will be solved very easily. Now first point about the virtual count. First point about the virtual count is that it can only be applied if open loop gain is infinite. It can only be applied, it can only, I am just writing down the point, it can only applied when open loop gain and operational amplifier possesses this quality, that means open loop gain of the operational amplifier is infinite. Okay, now one of the second point regarding the virtual count is that in the negative feedback it can only be applied on the negative feedback, and it can only be applied in the case of the operational amplifier in the linear region, not in the saturation region. And all of you know that the op-amp operate in the linear region in the case of the negative feedback, and whenever it operates in the amplifier mode, not in the oscillator mode. So in the case of the negative feedback, I am just writing down the condition for the virtual count. Okay, so in the case of the negative feedback, V0 by Vin, that is the equation, V0 by Vin equal to A divided by 1 plus A beta. Beta is the feedback factor. Okay, so this is the second point. Next, in the linear region of the operational amplifier, I have discussed what is linear region of the operational amplifier. So in the case of the linear region, your output voltage is gain into differential voltage. Okay, so your Vd is nothing but V0 divided by A. Okay, So your Vd is nothing but V0 can also be represented by this equation. V0 can also be represented by this equation, A into V in divided by 1 plus A beta, okay, into 1 by A. Okay, hope you can understand this equation very easily. Now if you just simplify this equation, this is V in divided by 1 plus A beta. Okay, so I have already said in the previously that the virtual ground concept can only be applied when the open loop gain of the infinite. Now if the open loop gain is infinite, then you can say that limit A tends to infinite, okay, your Vd is equal to, as this gain is infinite, this term will be very much high, so Vd will be 0. So as Vd will be 0, then you can say that your V plus voltage is equal to V minus voltage. Okay, so in the case of the virtual ground, this is the important concept, that your sorry, V plus, voltage of V plus is equal to V minus. So this is the concept of the virtual ground. The virtual ground is your V plus voltage, that means in a non-inverting terminal voltage is almost equal to the, not almost, is exactly equal to the inverting terminal voltage if the open loop gain of the op-amp is infinite and the op-amp is operating into the linear region and in the case in the negative feedback. Okay, next. Now two most important point you must remember in the case of the virtual ground, that the open loop gain is infinite and the op-amp must operate in the negative feedback. Now in the case of the negative feedback, positive feedback, the gain actually reduces. In the case of the positive feedback, why virtual ground concept is not applicable? Because gain is increases. Now at gain is increases, all of you know that this linear region is no longer operated by the op-amp. Op-amp is operate in the saturation region. Now in the saturation region, there is no increase or decrease of the voltage. Voltage is actually saturated, so op-amp is no longer in the mode of the amplifier. So that's why this concept cannot be applied. So this V plus and V minus is equal. That means that we can think of that that if this is your op-amp, negative and positive, so this is, so these two terminal voltage are equal. These two terminal voltage are equal means these two terminal are effectively sorted. We can think of that these two terminal are effectively sorted with each other. Okay, so that is the concept of the virtual ground. Okay, so this is your V0 and this is your Vd. Okay, so Vd is 0, that means these two terminal are effectively sorted. So this is now we can see how this virtual ground concept is being implemented in the case of a, with the help of a circuit diagram. Okay, now look at this circuit diagram. Feedback is in the negative terminal. This is the negative terminal voltage. This is the negative terminal voltage. So we can think that the output voltage, sum of the portion of the output voltage is feedback to the negative terminal. So this is a case of the negative feedback. Okay, so first point about the virtual ground is that this is the case of the negative feedback. Okay, this is the first point. So negative feedback, as there is a negative feedback, so we can actually apply the virtual ground concept. So this V plus, this is the V plus voltage and this is the V minus voltage. So V plus voltage is actually, you can see that V plus voltage is ground, so 0 volt. So you can think of that this terminal voltage, this terminal voltage, that means the V minus voltage is also 0 volt because of the virtual ground. So just by applying the property of the virtual ground, we can say as the V plus voltage is 0, so V minus voltage is also 0 in the concept of the virtual ground. Okay, so current is I have said in the case of the op-amp that no current is drawn by the op-amp. This is the 0 ampere. So current is actually flown through by this path I. Okay, by this path. So I equal to V in minus 0 divided by R in. So I equal to just V in divided by R in. Okay, so also the I can also be represented as terms of the output. That means this is the V0 and this is the 0 volt. So this current is flowing through here and this current is also flowing through here. So I am just writing this current equation as V in minus 0 divided by R in, and this current equation as V0. This is the voltage, okay, 0 minus V0 divided by RF. So 0 minus V0 divided by RF is equal to minus this current is also equal to this current. So this is V in divided by R in. So I am just again explaining this. I am just removing all this. So as this point potential is 0 volt, this point potential is also 0 volt. So whatever current is flowing through this current will be flowing through this. The equation for the current flowing through this is equal to the current is flowing through this terminal to this terminal. So V in higher potential to lower potential. So V in minus 0 divided by R in, and current is also flowing. I have assumed this current, no current is flowing to this terminal. So all of the current that has been generated from here is flowing through this terminal. So current is flowing actually from this node to this node. Actually this node potential is 0 volt and this node potential is V0. So 0 minus V0 by RF, and this is equal to V in divided by R in. Okay, so just simplifying this equation, V0 divided by V in equal to minus RF divided by R in. Okay, so this actually depends on the external resistance, not on the internal circuitry. So this depends on, gain is actually depends on external resistance. So this is the process by which we can apply the virtual ground concept to calculate the gain of the amplifier or gain of the operational amplifier in details. Okay, so this is all about the virtual ground concept. Hope you understand this, and just apply this concept to different problem, and your problem will be very much easy to solve with the help of this concept. Okay, so moving forward, next concept we will discuss some of the specification of the operational amplifier. That means the input bias current, input offset voltage. What do you mean by the offset voltage, offset condition, bias current, like that. Okay, okay, so moving forward, now we will discuss some of the specification of the operational amplifier. So the first specification is the input offset voltage. Now what do you mean by the input offset voltage? Now in the case of the first stage of the operational amplifier, I have said that first stage of the operational amplifier is dual input balanced output, dual input and balanced output stage. Now in the case of the dual input balanced output stage, I have also drawn the diagram like this. So this is your diagram, something like this. Okay, so this is the two transistor and this is the two collector. Output is being taken from this two terminals. So this is your V0. Okay, so this will be your voltage V1 and this will be your voltage V2. This is the two input voltages. Now in the case of the operational amplifier, I have said that your output voltage will be proportional to, 1 minute, your output voltage will be proportional to the difference between these two voltage applied at the two input. Okay, now this is true if both the transistor is identical. If both the transistor is identical in all aspect, identical in all aspect, both the transistor. Okay, both the transistor is identical in all aspects, but practically both the transistor cannot be exactly alike. Okay, so now the generation point, or why we study the input offset voltage, the point is that practically for the case of the first stage of the operational amplifier, that means the dual input balanced output differential amplifier case, there is a input voltage V1, input voltage V2, output voltage V0. Now in the case of the Opamp, we know that the output voltage is proportional to, that means V0 equal to some gain into the difference between these two voltages. This is true, but this is true when the transistor is identical. Both this transistor is identical in all aspects, but practically both the transistor cannot be exactly alike. So the problem arises that V0 will not be equal to 0 when V1 is equal to V2. That means if you give the same input both the terminal, then also your output will not be 0, but it supposed to be 0 when you give the same input to the two input terminal of the operational amplifier. So this is the generation point of your input offset voltage. Now the another condition can also be happens that V0 will be 0 when your V1 will be not equal to V2. So this is the two case for the input offset voltage and also case of the output offset voltage also. Okay, so these 2 points you must remember that these two transistor is not identical in practically, not theoretically, but practically both the transistor cannot be exactly alike. So that's why your V0 will not be equal to 0 when V1 is equal to V2, but is supposed to be 0 according to the theoretical definition. And also your V0 equal to 0 when V1 is not equal to V2. That is also cannot be true according to the theoretically. But practically it happens. So this is the practical specification of the operational amplifier. So what happens? The graph actually looks like the practical graph, theoretical graph actually looks like something like this. This is the actual graph of the operational amplifier. Okay, but practically what happens, the graph is something not like this. The graph is not like this. Graph is look like this. The graph is look like this. There is a 2 point of intersection. First point of intersection is here and second point of intersection is here. So this is your V0 and this is your VD. Okay, so this is your V0 and this is your VD. So you can easily say that your output voltage is not equal to 0 when your V1 is equal to V2, or the output voltage is equal to 0. That means when V1 is not equal to V2. So this is the point. This is the point. That means your this will be your output voltage. So output voltage is 0, but the difference between these voltages, so this point you just remember this point is the your input offset voltage, that is represented by Vi0. Now if you just define the input offset voltage, how do you define the input offset voltage? Now the input offset voltage is defined that amount of voltage which must be applied. This is the difference. This is the difference. So Vd is nothing but V1 minus V2. So you must apply this difference voltage, this amount of voltage to the difference voltage to the operational amplifier, so that your output voltage is equal to 0. Now the range of this voltage is, if you just define the range of this voltage, the range of this voltage is from 6 millivolt to 15 microvolt. This is the range of the input offset voltage. Now I am just going to explain it in a very simple manner. Just if anyone want to define the input offset voltage, now in the input offset voltage is that amount of voltage that must be applied between the two input terminal of the op-amp to make the output 0. Okay, that means it's supposed to be that whenever the input voltage is 0, both the input voltage is 0, the output voltage is also 0. But practically it is not happened due to the not identical mismatch of the transistor. So if this voltage, we apply some amount of voltage between the two terminal of the operational amplifier, so that your output voltage will be 0. So that voltage is called the input offset voltage. Okay, so that is the generation point of the input offset voltage, and graphically this point is there. Graphically this point is here. Now what do you mean by the output offset voltage? The second point is the output offset voltage. Now what do you mean by the output offset voltage? Now the output offset voltage, it this voltage, that means that amount of voltage whenever your input is 0, whenever both the input, this is your op-amp, this is negative positive. Now if we just short these two terminal, the what will be the output voltage? The output voltage is supposed to be 0. That practically the output voltage is not 0. There is some amount of voltage at the output, that is not 0. So that amount of voltage, that some amount of voltage that is generated at the output, that voltage is called the output offset voltage. Now graphically how it look like, graphically this point is here, this point, this point means your output, this is your V0, this is your Vd. So you can say there is some amount of output voltage whenever your input, this is the input, this input is 0, input characteristics, input axis is 0. Okay, that means we are making V1 equal to V2 equal to 0, but your at that point your output voltage is not 0. You can see easily that your out Vd equal to 0. Now Vd equal to 0, this axis Vd equal to 0 means V1 equal to V2 equal to 0. But at that point of time your V0, your V0 is not equal to 0. V0 is supposed to be 0 here, V0 is supposed to be 0 here, but it is not supposed to be 0. There is some amount of voltage, this voltage. So this voltage is called the output offset voltage. Now that means both transistor must be identical. For this case here both the transistor is not identical, that's why the if we sorted the both the input terminal, the output voltage is exactly not equal to 0. Okay, so the output voltage can be represented by, the output voltage is not A into V1 minus V2, this I am just writing this, the output voltage supposed to be, the output voltage supposed to be A into V1 minus V2. This is our theoretical case, but practice this is means V0 equals to, I am just writing this equation, A1 V1 plus A2 V2. Okay, if A2 is minus A1, then A2 is minus A1, then this equation will be valid. But practically this equation, that means for this case to be happen, transistor both the transistors should be identical, but practically both the transistors should not be identical. Then we go for this equation, V0 equal to, whenever we study the CMRR, then we see this kind of equation, that means V0 equals to A1 V1 plus A2 into V2. Okay, now this equation is same as this equation. If we put just A2 is minus of A1, if A2 is minus of A1, this equation is valid, and this equation valid for the ideal case whenever both the transistor will be equal. But practically this equation is valid, A1 V1 plus A2 V2, due to the mismatch of the transistor. Okay, next is the input offset current. Now what do you mean by the input offset current? Input offset current. Now the input offset current, we know the configuration is something like this. This is the configuration. Okay, so this is the voltage V in 1, this is the voltage V in 2, and this is the output voltages. This is the transistor Q1, this is the transistor Q2, and the current, this is the base of the both the transistor. Now the base of the both the transistor, current is entering between the both of the transistor base is IB1 IB2. This is the base terminal, this is the collector terminal, this is the emitter terminal. Now for the amplifier, there is some amount of base current. Now the base current in the case of the operational amplifier, I have said that no current is drawn by the operational amplifier input, or no current is going into the operational amplifier. That means the base current should be 0. Now how the base current would be 0 in the case of the transistor? Now the base current should be 0 in the case of the transistor whenever your beta is very high. Whenever your beta is very high, now we have studied that if the beta is very high, then your base current will be 0. This is the case how this op-amp input current will be 0. Now both the transistor Q1 or Q2 are practically different. I have already said previously that both the transistor Q1 or Q2 are practically different. Theoretically that should be equal, but practically if you try any amount of thing, both the transistor cannot be practically just matched with each other. Okay, so this IB1 IB2 is not equal to 0. There is due to the mismatch of transistor. So this is the input offset current, that means the I0. Theoretically this current should be 0. So we know what amount of current is greater, which amount of current is lower. So practically there is a flow of current into the op-amp due to the mismatch of the transistor. So range of this current is actually I0. range of this current is 200 nanoampere to 6 nanoampere. Okay, so I'm just again repeating what is input offset current. Input offset current is that theoretically what happens if this is your operational amplifier. I have said that the current drawn both this terminal is 0 ampere. Now inside the op-amp, this is your V in 1, this is your V in 2, but inside the op-amp, this is the actual case. So this is the IB1 and IB2 that is corresponding to this 0 ampere. Now to make this 0 ampere, your beta should be very high, transistor of the beta. So that is also okay. But what happens, both the transistors should be practically, theoretically matched, but practically their two transistors are not matched with each other. So that's why the current drawn by the op-amp is not actually 0. There is some amount of current drawn by the op-amp, and that amount of current is called the input offset current. Now the input offset current, what is the equation for the input offset current? Equation for the input offset current, just the difference between these two base current. That means IB1 minus IB2. So this is the input offset current. So next is the input bias current. So input bias current is very easy. Input bias current. This is the sum of the specification of the op-amp. So input bias current. Input bias current is nothing but the average of these two current. This is a one kind of specification. That means IB1, IB2 divided by 2. Due to the mismatch of the transistor, I am again repeating, due to the mismatch of the transistor in the differential amplifier stage, the op-amp current drawn by the op-amp is theoretically 0, but practically due to the mismatch of the transistor, current drawn by the two terminal of the op-amp is not equal to 0. There is some amount of current drawn. That current drawn, difference between this is input offset current, and the average between the average of these two current is bias current. Okay.